From the RSNA, this is the Radiology Artificial Intelligence Podcast. My name is Paul Yee, and I'm a radiologist and co-host of the podcast.
And my name is Ali Tijani, and I'm a radiologist and co-host of the podcast. Each month, we dive into the hottest topics in radiology AI and talk with leading experts, thought leaders, and movers and shakers in the field.
Welcome to Radiology AI Papers in a Capsule. I'm Bardia Khosravi, your host, member of the Training Editorial Board, and assistant podcast editor for Radiology Artificial Intelligence Journal. Join us for a dynamic podcast series exploring the latest peer-reviewed research published in our journal. We're here to break down cutting-edge AI studies in radiology with clear, concise, and objective summaries. Every episode is AI-generated, human-verified, and packed with scientific rigor to keep you informed and inspired. Our mission is to make AI research in radiology accessible to all while upholding highest scientific standards. We'd love to hear your thoughts. Share your feedback with us to keep this series vibrant, relevant, and top-notch for all our listeners.
Welcome to the second episode of Radiology AI Papers in a Capsule. Today we're discussing work by Urquetti and Venkotrigoven, co-first authors from Italy and the Netherlands.
Their paper addresses a fundamental challenge in using brain MRI for Alzheimer's disease assessment. They've developed an extension of a machine learning model called NeuroHarmony that addresses scanner-related variability in brain volumetric data.
This is particularly important because differences in MRI scanners and acquisition protocols can significantly affect the consistency of brain volume measurements. These inconsistencies present a major barrier to the clinical implementation of quantitative brain assessment tools that could aid radiologists.
And the authors have found a clever way to harmonize data from scanners that weren't even included in the original training. Let's dive into the details of this approach and why it matters for clinical practice.
Before we get into the methodology, could you explain why scanner harmonization is so critical in neuroimaging? I understand that radiologists primarily assess brain atrophy visually, so why is quantitative assessment gaining traction?
That's an excellent question. Visual assessment is indeed the current standard, but it's inherently subjective and prone to variability between readers. Quantitative imaging markers like brain volumetric measurements provide objective metrics that can increase diagnostic confidence and potentially detect subtle changes earlier.
So these quantitative methods could potentially improve patient outcomes. What specific challenges do scanner differences introduce?
When you scan the same person on different MRI machines, you can get significantly different volume measurements simply due to variations in field strength, hardware configurations, and acquisition parameters. Studies have shown volumetric differences of up to 15% between scanners, which is substantial when you consider that disease-related atrophy might only be 2 to 5% annually in Alzheimer's disease.
That variability could easily obscure actual disease-related changes. I imagine this becomes even more complicated when trying to implement automated tools across different clinical settings.
Precisely. Previous harmonization approaches like combat or deep harmony typically only work for scanner models they've been trained on. Some even require the same individuals to be scanned on multiple systems, which isn't feasible in clinical practice. The original NeuroHarmony model addressed this by using image quality metrics to predict corrections for new scanners, but it was primarily developed for healthy individuals.
And I would guess that disease pathology itself might affect those image quality metrics. So a model trained on healthy controls might not perform as well for patients with Alzheimer's or other dementias.
That's exactly the gap this paper addresses. The authors recognize that the interaction between disease pathology and image quality metrics needed to be accounted for in the harmonization model.
So what's the key innovation in their approach? How does this multi-class extension of NeuroHarmony differ from the original model?
The foundation is still the NeuroHarmony framework, which uses random forest regression to predict corrections needed to harmonize volumetric data. But the key innovation is how they account for cognitive status during model training and prediction.
Can you walk us through how they implemented this?
First, they collected an impressive data set spanning 11 cohorts, 43 scanners, and over 20,000 participants with varying cognitive status. healthy controls, subjective cognitive decline, mild cognitive impairment, and Alzheimer's disease. They processed all T1-weighted MRI scans with FreeSurfer to extract brain volumes and used the MRI-QC tool to generate image quality metrics.
And these image quality metrics are essential to the approach, right? They're what allows the model to generalize to unseen scanners?
Exactly. The key insight of NeuroHarmony is that scanner-related batch effects correlate with these measurable image quality characteristics. For training, they first harmonized volumes using Combat, which requires knowing which scanner each image came from. Then they trained a random forest model that could predict those harmonization corrections using only the image quality metrics.
But how does the multi-class approach specifically account for disease status?
They made two crucial modifications. First, they dichotomized cognitive status as either no cognitive impairment, healthy controls and subjective cognitive decline, or cognitive impairment, MCI and Alzheimer's. This simplified categorization means they don't need a precise clinical diagnosis during implementation, just a general cognitive status.
That seems more practical for clinical workflows. What was the second modification?
They used a technique called synthetic minority oversampling to ensure balanced representation of both cognitive groups during training. This prevents the model from being biased toward whichever group had more training data and ensures that the image quality metrics are equally representative of brains with and without neurodegeneration.
Did they compare this approach against other alternatives?
Yes, they systematically compared 3 approaches. The normative model trained only on individuals without cognitive impairment. An inclusive model trained on mixed data, but without their multi-class extension. And their proposed multi-class model. They evaluated each using cross-validation experiments at both the scanner and participant levels.
And what metrics did they use to evaluate performance?
They developed a measure called marker concordance to assess how well each method removed scanner-related differences. This measures the similarity of brain volume distributions between scanner pairs after harmonization. They also assessed how well disease-related signal was preserved by looking at the classification performance between healthy controls and Alzheimer's patients.
So, what did they find? Did the multi-class approach outperform the alternatives?
The results were quite compelling. The multi-class NeuroHarmony model achieved significantly higher marker concordance compared to the normative model trained only on controls.
That suggests it was better at removing scanner-related effects. But what about preserving the disease-related signal? That's crucial for clinical utility.
That's where the results were most impressive. The multi-class model preserved disease-related signal much better than the inclusive model. When looking at the area under the ROC curve for classifying healthy controls versus Alzheimer's patients, the multi-class model showed minimal signal loss compared to the inclusive model.
Those results suggest that the inclusive model was removing disease-related information along with the scanner effects. Was there a difference in performance between scanners that were included in training versus new unseen scanners?
Yes, and this highlights both the strength and an ongoing challenge. Marker concordance was better in scanners seen during training, concordance more than 0.97, than in unseen scanners, concordance less than 0.79. This means the model performs excellently for known scanner types, but still has room for improvement with completely new scanners.
That's still impressive generalization to new scanners. Did they look at which brain regions were most affected by harmonization?
They did find that across all harmonization approaches, the amygdala and hippocampi showed the best classification performance. This aligns with our understanding of Alzheimer's pathology, where these structures show early and significant atrophy.
What about limitations? Every approach has trade-offs.
One limitation they noted was that their approach may still remove some disease-related signal in the presence of diagnostic class imbalance across scanners. There's also the practical challenge of determining cognitive status during routine clinical workup, which would be needed to implement the model.
Did they suggest any approaches to overcome that implementation challenge?
They propose that machine learning models could potentially be used to predict cognitive status from the MRI itself. They even suggested developing multitask models that could jointly harmonize and predict cognitive status, though that would require further research.
So, what are the key takeaways for radiologists and researchers in this field?
I think the most significant contribution is demonstrating that we can successfully harmonize volumetric brain MRI data, even from scanners not included in training. This opens the door for more reliable quantitative assessment tools that could augment radiological evaluation of neurodegenerative diseases.
And the multi-class approach specifically addresses a key gap in previous harmonization methods by accounting for disease-related effects on image quality metrics. This seems essential for clinical translation of these tools.
Absolutely. While there's still work to be done to improve performance on completely unseen scanners and address implementation challenges, this represents a significant step toward enabling quantitative neuroradiologic assessment of Alzheimer's disease across diverse clinical settings.
Thank you for this illuminating discussion. For our listeners who want to learn more, you can find this paper in Radiology, Artificial Intelligence, Volume 7, Issue 1. There you can read more about their extensive validation across 11 international cohorts. Don't forget to follow us on social media at radiology_AI.
We hope you've enjoyed this episode of the Radiology Artificial Intelligence Podcast. Shout out to Yuri Ishimchisen for our podcast music and to the RSNA podcast staff.
Email us at podcasts@rsna.org anytime with questions, feedback, or suggestions.